A young world forms within a swirling disk of dust, ice, and rock that circles the early sun. The material in this disk moves through a complex ballet of collisions, mergers, and gravitational interactions. Within this environment, small particles fuse into pebble-sized bodies. Pebble clusters grow into kilometre-scale, around 0.6-mile objects, and these objects evolve into larger planetesimals. Over millions of years, these bodies combine through repeated impacts, assembling a glowing sphere of molten silicate magma. This sphere becomes Earth approximately 4.54 billion years ago. Its surface radiates enormous heat, with temperatures soaring above the melting point of nearly every mineral known today. Magma covers the planet in vast oceans of liquid rock, shifting in slow currents driven by convection within the mantle. Each new arrival from space, whether a small rocky fragment or a mountain-sized body, releases tremendous energy, stirring the molten surface and injecting more heat into the interior. The bombardment rate remains extremely high during this stage, a natural consequence of planetary formation within a dense disk of solids. Around this young planet, an atmosphere forms from outgassing and vaporized material. It thickens with steam, carbon dioxide, carbon monoxide, and abundant sulfur-bearing gases from persistent volcanic activity. These compounds give the sky a dense copper-red or orange hue, with light passing through layers of mist, aerosols, and mineral-rich vapor. As atmospheric pressure grows, clouds form frequently, rising through currents of heat that escape the planet's deep interior. Within this dynamic environment, Earth continues to accumulate mass. A large planetary embryo develops within a nearby orbit. Its path gradually shifts through gravitational interactions with the Sun and other growing worlds. This body, later named Theia, approaches Earth over time, eventually following a trajectory that intersects directly with the young planet. Their encounter reshapes Earth's entire outer structure. The collision between Earth and Theia releases energy on a scale far beyond ordinary planetary impacts. Their outer layers mix and vaporize into a hot, rotating cloud of silicate-rich debris. This material orbits Earth as a wide, luminous ring. Within this ring, particles collide gently and merge through gravitational attraction. Over thousands of years, these particles form a spherical body, the Moon. The new Moon circles close to Earth, creating strong tidal forces that stir the molten surface and the mantle beneath it. These tides distribute heat, influence rotation, and shape the early evolution of the planet's crust. As Earth turns on its axis, the Moon raises large tidal bulges within the magma oceans, guiding the movement of heat and altering how the planet cools. The impact with Theia sets the stage for a long period of thermal evolution. Vaporized silicates condense and rain back to the surface. Molten regions mix thoroughly, producing a more homogeneous mantle composition. As heat escapes into space through radiation, the surface gradually cools. A thin crust forms from basaltic rock, fragile at first, yet increasingly stable as temperatures continue to fall. Volcanic eruptions still rise through this crust, delivering gases from deep within and maintaining a thick atmosphere dominated by steam and carbon dioxide. As cooling progresses, the crust strengthens enough to preserve early minerals. Among the first crystals capable of surviving the planet's intense heat cycles are zircons, zirconium silicate grains that form within cooling magma or in interaction zones between molten and solid rock. Some zircons record ages of 4.38 billion years, offering evidence for surprisingly early crust formation. Their internal isotopic structures also indicate interaction with liquid water, meaning that surface environments occasionally reach temperatures low enough for water to exist in stable form. These early interactions between rock and water play an essential role in shaping Earth's geochemical cycles. Water alters minerals, transports ions, and contributes to the formation of secondary rocks. Even in small quantities, water influences the viscosity of magma, the chemistry of volcanic gases, and the rate at which the crust can thicken. Geologists study trace elements and oxygen isotopes within zircons to infer details of these ancient processes. Their findings help reconstruct a time period with limited direct rock record, offering rare glimpses into the earliest stable surfaces. The source of this water arises from multiple pathways. Carbonaceous asteroids provide hydrated minerals capable of releasing water during impact or metamorphic heating. Many of these asteroids originate in the outer regions of the young solar system, with chemical signatures that match Earth's water more closely than those of comets. Each impact contributes additional volatiles, gradually increasing the planet's water inventory. At the same time, Earth's interior contains hydrogen incorporated during formation. As the mantle melts and circulates, this hydrogen combines with oxygen to create water vapor. Volcanic outgassing delivers this vapor into the atmosphere, where it accumulates and condenses as the surface cools. This internal source may have supplied vast amounts of water, complementing the contributions from external bodies. The cooling process unfolds in cycles. After a particularly large impact, the surface heats intensely, vaporizing water and silicates into the atmosphere. As the heat radiates away, vapor condenses again, producing immense rainfall. These storms last for centuries, with drops falling into lava fields and rising back as steam. Over time, repeated cycles of rain, cooling, and crust thickening allow liquid water to persist for longer durations. Oceans begin to gather within large basins, shaped by the planet's uneven crust. The formation of oceans influences atmospheric chemistry. Water absorbs carbon dioxide through dissolution and chemical reactions with newly formed crustal minerals. Basaltic rocks weather rapidly under these conditions, incorporating carbon into carbonates and reducing atmospheric pressure. This early carbon cycle moderates surface temperature, guiding the planet toward long-term stability. Through these interactions, Earth establishes the first version of a regulatory system that will persist, with variations, for billions of years. The Moon's gravitational influence also contributes to the planet's evolution. Early tidal forces generate heat through friction within the mantle. This additional heat alters convection patterns and contributes to crust formation in ways that differ from other terrestrial planets. The Moon also shapes Earth's rotation, gradually lengthening the day from a rapid early period to a slower rhythm. These changes influence atmospheric circulation and the distribution of surface heat. As crust thickens, volcanic structures grow across the surface. Mantle plumes rise through the lithosphere, producing large volcanic fields and extensive lava flows. Each eruption releases more gases and contributes to the atmosphere's evolving composition. Sulfur dioxide forms aerosols that scatter sunlight, influencing temperature. Carbon dioxide builds a powerful greenhouse effect, maintaining warmth even as the sun shines with lower luminosity than it will in later ages. Earth's early magnetic field strengthens as the core differentiates. Convection within the metallic core generates a dynamo effect that produces a protective magnetosphere around the planet. This shield reduces atmospheric erosion by the solar wind and helps retain the gases essential for climate and geochemistry. A stable magnetosphere emerges as a key factor in the planet's long-term habitability. Before continuing, the narration slows slightly, and an invitation fits naturally within the flow. Before we go deeper, if you enjoy exploring the quiet wonders of the cosmos like this, consider subscribing and leaving a comment with where you're listening from and what time it is there. It helps this channel grow, and it keeps these journeys alive. Across millions of years, the surface evolves from a magma-dominated world into a landscape with both molten and solid regions. Stable crust increases in thickness, allowing more complex interactions between the surface, atmosphere, and interior. Hydrothermal systems develop around volcanic regions. Water circulates through cracks in the crust, reacting with minerals and transporting dissolved elements back to the surface. These systems create environments rich in chemical gradients, setting foundations for future geochemical complexity. By the later stages of this era, oceans spread widely across the surface. Basins fill with water delivered from both internal and external sources. The early atmosphere transitions from rock vapor to a mixture of steam, carbon dioxide, nitrogen, and sulfur gases. Dense clouds move across the planet, producing frequent rainfall and influencing temperature regulation. Light from the sun scatters through these clouds, illuminating a world with shifting hues of red, gold, and grey. Earth's crust continues to reorganize as tectonic activity grows more dynamic. Protocontinental fragments emerge through volcanic buildup and crustal thickening. These land masses drift, merge, and fragment under the influence of mantle convection. Although small and short-lived, these early continents influence ocean circulation, chemical weathering, and atmospheric composition. Silicate weathering on land contributes further to carbon burial and temperature control. Mineral formation increases in diversity as the planet cools. Zircons remain among the most valuable geological time capsules, preserving information about temperatures, water presence, and crustal conditions. Other minerals form in response to hydrothermal alteration, volcanic eruption, and sedimentation in the earliest shallow seas. Each mineral type offers clues about the evolving environment, providing scientists with a means to reconstruct conditions that shaped the planet's infancy. Earth progresses steadily toward a state capable of supporting more complex atmospheric and surface interactions. Heat flow decreases as the mantle cools. Volcanism shifts from planet-wide magma oceans to more localized volcanic fields. Oceans grow deeper, and atmospheric pressure gradually stabilizes. Through these transformations, Earth develops the essential frameworks for long-term climate cycles, continental evolution, and the emergence of chemical pathways that will eventually support life. In this early chapter of deep time, the planet advances from molten origins toward a state of increasing stability. Layers form, oceans gather, minerals crystallize, and the first foundations of habitability arise. Across hundreds of millions of years, Earth becomes a world with the structure, chemistry, and dynamic behavior capable of sustaining the next major transformation, the arrival of a persistent atmosphere shaped by geological and biological processes. Earth enters a new chapter during the Archean Eon, from roughly 4.0 to 2.5 billion years ago. The planet shows clearer structure, with oceans spread across its surface and volcanic arcs rising above the water in scattered chains. The atmosphere thickens as volcanic gases pour upward. Methane, nitrogen, carbon dioxide, hydrogen sulfide, and water vapor create a dense, richly colored sky. Free oxygen remains present only in extremely small trace quantities, far below the level required to influence surface chemistry or climate. This mixture gives the air a warm, hazy character, shaped by hydrocarbon particles that scatter sunlight into amber and copper tones. Methane plays a central role in this stage of Earth's evolution. Volcanic emissions, hydrothermal reactions, and early biological processes enrich the atmosphere with it. Methane traps infrared radiation with great efficiency, forming a greenhouse blanket that preserves warmth even while the young sun shines with roughly 70% of its current luminosity. Nitrogen, abundant in volcanic gases, accumulates steadily, forming the bulk of atmospheric pressure. Researchers studying ancient isotopic signatures, including work by James Casting and colleagues, have reconstructed this early atmosphere, revealing a world with a climate shaped strongly by methane feedbacks and intense volcanic activity. Across Earth's surface, tectonic processes continue to reorganize crustal material. Early proto-continents form through the thickening and stabilization of buoyant granitic crust. These landmasses rise above sea level as mantle convection pushes hot material upward beneath them. Their surfaces host a combination of volcanic fields, weathering environments, and shallow coastal seas. The size and shape of these proto-continents change frequently through accretion of island arcs and reworking by mantle plumes. The Archean crust records important signs of this evolution. Rocks from regions such as the Pilbara Craton in Australia and the Barberton Greenstone Belt in South Africa contain some of Earth's oldest preserved geological sequences. These ancient terrains reveal processes such as subduction-like recycling, plume-driven magmatism, and early sedimentary cycles. Geologists identify signatures of shallow water environments, volcanic ash layers, and hydrothermal systems that indicate dynamic interactions between ocean, crust, and atmosphere. Within these settings, life emerges with distinctive geological footprints. Stromatolites, layered structures built by microbial communities, appear in the rock record around 3.5 billion years ago. These formations grow as microorganisms trap and bind fine sediment, creating domed, laminated buildups in shallow marine environments. Their presence signals thriving microbial mats that harvest energy from their surroundings. Many stromatolites rely on photosynthesis, although early forms often follow pathways that operate efficiently in oxygen-poor conditions. These microbial communities participate actively in Earth's early chemical cycles. One major pathway is nitrogen fixation, the ability of certain microorganisms to convert atmospheric nitrogen into biologically accessible ammonia. This process requires specialized enzymes and supplies essential nutrients to ecosystems that rely on nitrogen for growth. Through nitrogen fixation, Archean microbes introduce a powerful mechanism for distributing nitrogen from the atmosphere into ocean chemistry and sedimentary environments. The carbon cycle also gains structure through biological and geochemical processes. Methanogenic microorganisms produce methane through the breakdown of carbon compounds, enriching the atmosphere with a greenhouse gas that plays a central role in maintaining surface warmth. Other microbes incorporate carbon dioxide into organic molecules through photosynthetic and chemosynthetic pathways. Sedimentary basins capture carbon through the burial of organic matter and carbonate minerals, linking the atmosphere and lithosphere through cycles that evolve in complexity across geological time. Hydrothermal vents along mid-ocean ridges and volcanic arcs provide environments rich in chemical gradients, minerals, and heat. These systems circulate seawater through fractures in the crust, altering its chemistry and delivering dissolved metals and nutrients back to the ocean. Many early microbes thrive in such settings, drawing energy from reactions involving hydrogen, sulfur, and iron. The Archean Ocean contains abundant dissolved iron, producing greenish or bluish hues influenced by its chemistry. As protocontinents grow, their surfaces interact with the atmosphere. Weathering of volcanic and granitic rocks releases ions into rivers and shallow seas. These ions contribute to the early formation of carbonate minerals and influence ocean pH. Sedimentary layers accumulate around the margins of protocontinents, preserving chemical signatures that help reconstruct Archean climate and ocean composition. Studies of isotopes such as carbon-13, sulfur-34, and nitrogen-15 reveal patterns of microbial metabolism and atmospheric chemistry that define this era. The Archean atmosphere contains thick hydrocarbon hazes formed by photochemical reactions involving methane and sunlight. These hazes reduce the amount of solar radiation reaching the surface while still permitting strong greenhouse warming. Planetary scientists often compare this effect to the modern atmosphere of Titan, Saturn's largest moon, which hosts methane-rich air and organic aerosol layers. Ancient Earth, however, experiences conditions favourable for liquid water, widespread oceans, and active tectonics. Volcanic activity continues across much of the planet. Mantle plumes rise through the lithosphere, creating large basaltic provinces and sustaining hydrothermal circulation. These volcanic outputs replenish atmospheric gases and maintain the chemical composition of the Archean sky. Large volcanic islands form where plumes intersect the surface, eventually merging with protocontinents through tectonic motion. These growing land masses influence weather patterns, ocean currents, and sedimentation. Among the most significant developments during the Archean is the gradual expansion of microbial ecosystems. Microbial mats occupy tidal flats, lagoonal environments, and shallow seas. Their layered structures alter local environments by trapping sediment, producing organic matter, and modifying the chemistry of surrounding waters. Some microbes begin to release small amounts of oxygen through primitive forms of photosynthesis, especially those related to early cyanobacteria. Although atmospheric oxygen remains extremely low during this era, local microenvironments experience subtle enrichment, influencing the mineralogy of nearby sediments. Research into ancient rocks reveals early signs of oxidative weathering and trace oxygen activity. These signatures appear in minerals such as detrital uraninite and pyrite, which preserve information about surface conditions prior to the large-scale oxygenation events that will come later. These findings help scientists map the gradual transition of Earth's atmosphere long before oxygen reaches levels capable of transforming global chemistry. Within the oceans, iron cycles strongly influence Archean environments. Dissolved ferrous iron circulates through seawater, interacting with hydrothermal fluids and microbial processes. In certain regions, iron minerals precipitate out, forming layers that contribute to early banded iron formations. These deposits provide essential clues about ocean redox chemistry and microbial activity. Throughout the Archean, Earth's climate maintains a balance shaped by greenhouse gases, volcanic heat, ocean circulation, and microbial feedbacks. The methane-rich atmosphere provides a warm climate capable of supporting liquid water across much of the planet's surface. Protocontinents expand, oceans deepen, and chemical cycles grow in complexity. These conditions prepare the stage for the next major transformation, a shift driven by microbial photosynthesis that will gradually reshape the air, oceans, and minerals of the entire planet. The Archean world carries an atmosphere rich in methane and nitrogen, oceans alive with microbial communities, continents forming through tectonic processes, and chemical cycles that gain strength and stability. Through each of these steps, Earth advances toward its next major shift in planetary chemistry, the rise of oxygen. Earth enters a profound transformation around 2.7 to 2.4 billion years ago, a time when microbial evolution shapes the atmosphere in ways that alter the chemistry of oceans, minerals, and climate. Cyanobacteria, ancient microorganisms that thrive in shallow waters, develop a remarkable metabolic strategy known as oxygenic photosynthesis. Through this process, they use sunlight to split water molecules, releasing oxygen as a byproduct and capturing carbon in organic form. This innovation introduces a source of free oxygen with the potential to influence the entire planet. Cyanobacteria flourish in coastal mats, lagoonal waters, and shallow marine shelves. Their pigments absorb sunlight efficiently, and their cellular machinery channels the energy into biochemical reactions that drive carbon fixation. These organisms produce enormous quantities of oxygen over millions of years, releasing it steadily into seawater. Early oceans contain abundant dissolved iron and reduced sulfur compounds, both of which interact readily with oxygen. As a result, oxygen accumulates gradually while participating in widespread chemical reactions that shape marine sediments. One of the most striking records of this activity appears in banded iron formations, layered rocks composed of alternating bands of iron-rich minerals and silica. These deposits form as dissolved ferrous iron in seawater reacts with oxygen produced by microbial photosynthesis. When oxygen enters the water, it oxidizes ferrous iron to ferric iron, which precipitates as hematite or magnetite. These minerals settle onto the seafloor, creating layers that archive the evolution of early ocean chemistry. Banded iron formations from regions such as Western Australia, Canada, and South Africa stretch across hundreds of kilometres, hundreds of miles, and represent one of the most extensive mineral records of microbial influence on a planetary scale. As cyanobacteria continue to produce oxygen, the oceans gradually shift in redox state. Iron acts as a major sink, capturing oxygen in vast quantities. Reduced sulfur compounds also interact with oxygen, forming sulfate minerals through oxidative reactions. Each reaction draws oxygen into the geochemical system, regulating its accumulation in the atmosphere. For long periods, oxygen production and oxygen consumption maintain a balance shaped by microbial activity and the chemistry of seawater. Over time, sinks begin to fill and their capacity to absorb oxygen reaches equilibrium with microbial production. Once iron becomes sufficiently depleted in large regions of the ocean, the efficiency of oxygen removal declines. This shift allows oxygen to diffuse more broadly into seawater and eventually escape into the atmosphere. Around 2.4 billion years ago, atmospheric oxygen reaches a threshold that produces a fundamental transformation in atmospheric composition. Atmospheric oxygen interacts with ultraviolet radiation from the sun to form ozone, a molecule that accumulates in the upper atmosphere. The formation of an ozone layer influences the spectral character of sunlight reaching the surface and provides shielding for future biological innovations. Oxygen also participates in new chemical cycles involving carbon, sulfur, and nitrogen, reshaping the planet's oxidative balance. Methane, a potent greenhouse gas produced abundantly by methanogenic microorganisms, responds sensitively to increasing oxygen. Oxygen reacts with methane in the atmosphere to produce carbon dioxide and water, reducing methane concentrations substantially. This shift alters Earth's climate system. The Archean methane-rich atmosphere supports a warm global climate that balances the lower luminosity of the early sun. A reduction in methane decreases greenhouse warming, leading to cooler global temperatures. Researchers studying the Paleoproterozoic period identify signs of dramatic glaciations that follow this atmospheric transition. Geological formations from regions such as Canada and South Africa reveal glacial deposits at paleolatitudes that appear close to the equator. These deposits support a scenario in which ice sheets expand widely across the planet, forming global-scale glaciations often referred to as Snowball Earth episodes. During these episodes, ice advances across continents and sea ice grows across vast regions of the ocean. High albedo, the reflectivity of ice, reduces solar absorption, reinforcing cooling trends. Volcanic activity continues beneath thick ice sheets and beneath ocean ice, releasing carbon dioxide into the atmosphere. Over long periods, this buildup of carbon dioxide increases greenhouse warming, eventually shifting conditions toward melting and recovery. These cycles introduce major climatic oscillations that influence early life and the geochemical evolution of the planet. The Great Oxidation Event brings far-reaching consequences for mineral formation. New minerals appear as oxygen participates in reactions that create oxides, hydroxides, and sulfates. The diversity of Earth's mineral record expands significantly, supporting research by mineralogists such as Robert Hazen, who estimate a dramatic increase in mineral species following oxygenation. These new minerals store information about redox conditions, temperature, and fluid compositions, offering future scientists a rich archive of early planetary processes. Sedimentary rocks formed during this time preserve evidence for oxidative weathering on land. Although continental land masses remain relatively small compared to later eras, they contribute to carbon and sulfur cycles through interactions with the atmosphere. Weathering releases ions that enter rivers and oceans, enhancing the formation of sulfate minerals and carbonate sediments. These processes influence both ocean chemistry and atmospheric composition, reinforcing the shift toward an oxygen-rich world. Microbial communities respond to these changes in diverse ways. Cyanobacteria flourish in oxygenated surface waters, expanding their ecological range. Other microorganisms adapt to new niches created by gradients between oxygen-rich and oxygen-poor environments. Some anaerobic microbes thrive in deeper waters or within sediments where oxygen diffusion remains limited. The biological world grows more complex as metabolic pathways diversify in response to new chemical landscapes. Oxygen introduces energetic advantages for certain metabolisms. Aerobic respiration, which extracts energy from organic molecules using oxygen, provides far greater energy yield than anaerobic pathways. This increased efficiency supports more complex cellular structures and larger cell sizes, setting foundations for future biological innovations. Although multicellular life remains far in the future during the Great Oxidation Event, the metabolic groundwork for biological complexity emerges during this time. The atmosphere itself begins to take on characteristics that define modern Earth. As oxygen accumulates, light scattering shifts toward shorter wavelengths, creating conditions that favor blue skies during clear weather. The presence of ozone filters ultraviolet radiation, enabling future life to explore new ecological spaces with greater resilience to solar radiation. Climate cycles during the Paleoproterozoic continue to oscillate as greenhouse gases, volcanic activity, and solar luminosity evolve. Glacial advances and retreats leave widespread sedimentary deposits that record the extent of ice cover. Drop stones, large rocks carried by icebergs and dropped into marine sediments, appear in rock layers across several continents, marking the influence of floating ice. These features join geochemical indicators as evidence for planetary-scale glaciation. The Great Oxidation Event also influences the sulfur cycle. As oxygen reacts with reduced sulfur compounds, sulfate becomes abundant in the oceans. Sediments record this shift through changes in sulfur isotope ratios, with studies by geochemists such as Donald Canfield revealing patterns that trace the oxidation of sulfur during this era. These data help reconstruct atmospheric and oceanic conditions across hundreds of millions of years. Volcanic activity continues to provide carbon dioxide and other gases, maintaining a balance between greenhouse warming and the planet's reflective glacial surfaces. Over time, increasing solar luminosity contributes additional warming, helping Earth emerge from extended glaciations. Once ice retreats, oceans regain circulation patterns that support nutrient distribution, microbial productivity, and sedimentary deposition. The Great Oxidation Event stands as one of the most influential transitions in Earth's history. It introduces a long-lasting supply of free oxygen, transforms minerals and sediments across the planet, reshapes climate through interactions with greenhouse gases, and prepares the environment for future biological evolution. Cyanobacteria, through their photosynthetic activity, guide this global transformation and lay the foundation for ecosystems that will flourish over billions of years. Atmospheric oxygen rises in stages, with fluctuations tied to volcanic activity, biological growth, and ocean chemistry. Each rise influences climate and mineralogy. Each interaction between oxygen and geochemical sinks contributes to the gradual stabilization of an oxygen-bearing atmosphere. Through these cycles, Earth advances toward a world shaped by oxidative chemistry, biological innovation, and dynamic climate evolution. The sky gradually gains the clarity and spectral scattering that define its modern appearance. Oceans store oxygen in their upper layers. Mineral diversity expands, microbial ecosystems adjust to new conditions, exploring energy pathways that benefit from oxygen's powerful chemical potential. These combined forces shape an environment capable of supporting the next great transformations in life and climate. The Great Oxidation Event marks the dawn of an oxygen-rich Earth, guided by microscopic organisms that reshape the air, oceans, and rocks through their quiet, persistent activity. The stage now forms for complex chemistry, expanding ecosystems, and future worlds filled with new biological possibilities. Across Earth's deep timeline, the planet moves through intervals of remarkable climatic extremes. Among the most dramatic events are the global-scale glaciations that appear during the Paleoproterozoic, shortly after the Great Oxidation Event, and again during the Cryogenian period, hundreds of millions of years later. These episodes shape continents, oceans, atmosphere, and the evolution of early life. They arise from a combination of tectonic shifts, atmospheric chemistry, solar radiation, and feedbacks involving ice and albedo. Through each event, Earth displays a powerful climatic flexibility that echoes across billions of years. The Paleoproterozoic glaciations begin around 2.4 billion years ago, a time when oxygen from cyanobacteria influences atmospheric composition and methane levels shift accordingly. Methane holds tremendous greenhouse power, and changes in methane concentration alter global temperatures. Geological formations from Canada, South Africa, and other ancient terrains display glacial deposits at paleolatitudes that correspond to regions near the equator. These deposits include striated pavements, drop stones, and glacial tillites. Their position within the rock record indicates widespread ice coverage across continents that reside in warm, latitudinal zones. Such global-scale ice coverage arises through albedo feedback. When ice spreads over land and ocean, it reflects sunlight efficiently. This reflective surface increases the proportion of solar radiation that returns to space, reducing heat absorption. As temperatures decline, additional ice forms, which enhances reflectivity further. The cycle continues, creating a self-reinforcing system that extends glaciation across enormous regions. Once ice reaches certain thresholds, global temperatures shift significantly, allowing glaciers to advance across continents and sea ice to stretch from pole to pole. Atmospheric conditions support these transformations. During the Paleoproterozoic, the rise of oxygen influences methane chemistry. Oxygen interacts with methane through photochemical reactions, producing carbon dioxide and water vapor. Carbon dioxide provides greenhouse warming as well, although methane produces stronger effects per molecule. As methane declines, the greenhouse blanket surrounding Earth changes. With less heat retention, surface temperatures move toward levels that support ice expansion. Geological evidence indicates extremely thick ice sheets and marine ice capable of spanning entire ocean basins. The Cryogenian period, between roughly 720 and 635 million years ago, presents another major interval of global glaciation. This era includes two immense events often referred to as the Sturtian and Marinoan glaciations. Geological formations from Namibia, Canada, China, and Australia show consistent signs of low-latitude glacial deposits supporting the wide spatial extent of ice coverage. Tectonic reconstructions suggest that continents during this time cluster near the equator. Such arrangements influence global circulation patterns, ocean heat distribution, and atmospheric moisture content in ways that favor large-scale glaciation. Signatures of cryogenian ice appear in characteristic sedimentary structures. Glacial diamictites, sediments containing a mixture of boulders, pebbles, and fine-grained material, occur in sequences that transition sharply into carbonate layers known as cap carbonates. These cap carbonates form rapidly as glaciation ends, likely due to intense chemical reactions between atmospheric carbon dioxide and ocean surface waters. Their consistent placement above glacial deposits provides a reliable marker for Snowball Earth deglaciation events. Throughout these glacial intervals, life persists in environments that offer protection from extreme cold. Refugia, safe zones that maintain liquid water and suitable chemical conditions, exist in several forms. Hydrothermal vents along mid-ocean ridges create warm, mineral-rich water that circulates through the deep ocean. These systems support microbial communities that thrive on chemical energy rather than sunlight. Subglacial lakes form beneath thick ice sheets insulated by geothermal heat from Earth's interior. Meltwater channels move through ice, creating microenvironments with moderate salinity and temperature. Even within sea ice, pockets of brine create habitats rich in nutrients and microbial activity. These refugia sustain microbial ecosystems during extended ice coverage. Many microorganisms rely on chemosynthetic pathways that function independently of sunlight, allowing populations to persist in complete darkness. Photosynthetic organisms survive in thin regions of equatorial or coastal ice where sunlight penetrates. Cryoconite holes, small depressions on glacial surfaces filled with dust, microbes and meltwater, form ecological niches that host diverse microbial life. These microenvironments act as stable anchors for biological continuity during snowball conditions. Volcanic activity continues beneath ice sheets and within tectonically active regions. Volcanoes release carbon dioxide steadily into the atmosphere. During Snowball Earth episodes, carbon dioxide accumulates gradually because weathering rates on land decrease. Weathering ordinarily draws carbon dioxide out of the atmosphere through reactions between minerals and rainwater. Thick ice reduces exposure of continental rocks, slowing this process and allowing volcanic carbon dioxide to build over long time scales. This accumulation of atmospheric carbon dioxide plays a central role in the eventual exit from snowball conditions. As carbon dioxide reaches extremely high concentrations, its greenhouse effect amplifies significantly. Radiative forcing increases, trapping infrared energy efficiently and raising global temperatures. Over thousands to millions of years, this warming trend thins equatorial sea ice and eventually opens patches of open water. Once liquid water appears, the ocean absorbs more solar radiation, accelerating melting. A runaway greenhouse effect unfolds as ice retreats. Dark ocean surfaces absorb sunlight far more effectively than ice. As melt zones expand, absorption increases, reinforcing the warming trend. Melting accelerates across continents and ocean basins. The planet transitions rapidly from an ice-covered state to a globally warmer environment. Sedimentary layers record this moment of transformation in the form of cap carbonates. These thick carbonate layers form as atmospheric carbon dioxide interacts with surface waters enriched by glacial melt, precipitating minerals across wide continental shelves. The end of Snowball Earth episodes marks periods of intense climatic and ecological change. Oxygen production by microbial photosynthesizers resumes at higher efficiency as open waters return. Nutrient cycles restart as continental runoff increases. Oceans circulate fresh supplies of minerals and dissolved ions, supporting new biological growth. Paleoproterozoic glaciation contributes to the first major increase in atmospheric oxygen, while cryogeny and deglaciation sets the stage for the rise of multicellular life. During the cryogenian aftermath, chemical and isotopic signatures show increases in nutrients such as phosphorus and nitrogen within marine sediments. These nutrients support ecosystems with greater productivity. Ediacaran life, with soft-bodied forms representing early multicellular organisms, emerges shortly after the Marinoan glaciation. Their appearance aligns with the return of stable oceans, enriched nutrient levels, and greater availability of dissolved oxygen. Scientists analyze Snowball Earth episodes using multiple forms of evidence. Paleomagnetic measurements reveal the latitudinal positions of continents during glaciation. Carbon isotope ratios trace the interaction between the carbon cycle and glacial processes. Sulfur isotopes record oxidative changes that accompany rising oxygen levels and volcanically driven atmospheric shifts. Sedimentary facies, patterns of rock layers, display transitions between glacial deposits and post-glacial carbonates, marking the rhythm of glaciation and deglaciation. The global character of these glaciations highlights the sensitivity of Earth's climate system. Variations in atmospheric greenhouse gases, continental positioning, ocean circulation, and solar luminosity all contribute to climate dynamics. Feedbacks involving ice, albedo, and carbon dioxide amplify small changes into planetary scale shifts. These feedbacks continue to influence modern climate processes, offering essential insights into Earth's long-term environment. Snowball Earth episodes shape mineral formation as well. During icehouse conditions, ocean chemistry moves towards states that favor specific minerals. Iron-rich sediments, manganese deposits, and various carbonates accumulate in distinct layers. These minerals offer clues about ocean redox states, nutrient availability, and microbial activity. After deglaciation, cap carbonate layers provide a unique mineralogical archive of rapid chemical changes. Throughout each global glaciation, life adapts and persists. Microbial diversity expands within refugia. Genetic innovations evolve in environments shaped by extreme conditions. The resilience displayed during these episodes prepares ecosystems for later expansions in complexity. As ice retreats and climates stabilize, life moves into new ecological spaces with renewed vigor. Snowball Earth episodes stand among the most dramatic climatic events in planetary history. They demonstrate the profound influence of atmospheric chemistry, tectonics, and solar radiation on global temperature. Their legacy appears in geological formations across continents, in mineralogical signatures that trace ancient oceans, and in the biological innovations that flourish during periods of recovery. Through cycles of ice formation, greenhouse buildup, and rapid melting, Earth explores a full spectrum of climatic possibilities. Each glaciation leaves an imprint on the atmosphere, the oceans, and the biosphere. These episodes guide the planet toward new evolutionary chapters, preparing the stage for oxygen-rich oceans, complex ecosystems, and eventually the rise of animals. As Earth enters the late Proterozoic, oxygen in the atmosphere and oceans rises toward thresholds that allow a new kind of biology to flourish. Microbial life has shaped the planet for more than 2 billion years, steadily influencing the chemistry of seawater, sediments, and air. Through these slow transformations, the planet acquires a stable supply of free oxygen in surface environments. This oxygen becomes a powerful catalyst for evolutionary innovation, supporting metabolisms with far greater energy yield than earlier pathways. Oxygen reaches levels that allow the emergence of eukaryotic cells, organisms with internal membranes, a nucleus, and complex intracellular structures. These cells arise through one of the most significant events in evolutionary history, endosymbiosis. In this process, a larger host cell engulfs a smaller organism that carries energy-producing capabilities. Instead of digestion, the two establish a long-term partnership. The smaller organism becomes mitochondria, specialized structures that produce energy with remarkable efficiency through aerobic respiration. This symbiosis transforms biological potential. Mitochondria generate orders of magnitude more energy than anaerobic pathways, supporting larger cell sizes, more intricate internal architecture, and faster growth rates. With this energy source, cells evolve new cytoskeletal systems, behavioral strategies, and developmental patterns. Eukaryotic cells explore ecological spaces that enrich marine ecosystems and set the foundation for later multicellular life. As oxygen spreads into deeper ocean layers, ecosystems diversify further. The deep ocean, once dominated by chemical cycles involving iron, sulfur, and methane, begins to host organisms that rely on oxygen as an electron acceptor. This shift influences nutrient distribution, sediment biology, and ocean circulation. Oxygen expands the vertical structure of ecosystems, creating gradients from surface waters to deeper regions that host varied communities of organisms. These gradients encourage metabolic diversity and stimulate nutrient recycling. Near continental shelves and shallow seas, nutrient supply increases through weathering of rocks and the action of glaciers during cryogenian deglaciation. Rivers deliver phosphorus, nitrogen compounds, and trace metals into coastal regions, fueling microbial productivity. As nutrients flow into the ocean, primary production rises, generating organic matter that supports food webs with greater complexity. This growing energy throughput encourages the evolution of organisms with multiple cell types, coordinated tissues, and larger body structures. Around 575 million years ago, the first known large multicellular organisms appear in the fossil record. These ediacaran organisms inhabit shallow marine environments with stable conditions, moderate oxygen levels, and abundant microbial mats. Their bodies take diverse forms: frond-like structures, segmented ovals, quilted discs, and elongated shapes arranged with radial or bilateral symmetry. Many display soft tissues without mineralized skeletons, giving them delicate impressions in fine sediments. The ediacaran biota represents a major evolutionary exploration of form. Some organisms filter suspended particles, others absorb nutrients directly from seawater or microbial mats, and some glide slowly across surfaces. Each group contributes to an expanding set of ecological strategies. Their presence indicates the emergence of ecosystems with multiple trophic levels, reflecting a world with abundant energy, stable oxygen supply, and increased biological interaction. Deep ocean oxygenation strengthens through circulation patterns that deliver oxygen-rich waters to greater depths. Massive overturning currents carry surface waters downward along continental margins. These currents supply oxygen for organisms living far from sunlight, influencing the distribution of nutrients and the decomposition of organic matter. As deep regions receive oxygen, the burial of organic carbon increases, reinforcing atmospheric oxygen levels. This feedback supports long-term climate stability and encourages even greater biological activity. Mineral records from this time show changes that align with deep ocean oxygenation. Iron-rich sediments diminish as iron oxidizes in surface waters and precipitates before reaching deep basins. Sulfur isotopes shift toward values that reflect oxidative sulfur cycling. These geochemical signatures reveal oceans capable of supporting widespread aerobic processes, a key requirement for the expansion of complex life. With oxygen available in both surface and deeper regions, evolution accelerates. Cellular differentiation allows organisms to form tissues with specialized functions: protective coverings, digestive layers, contractile fibers, and sensory structures. Communication between cells strengthens, enabling coordinated movement and response to environmental cues. Body plans grow more intricate, reflecting the energetic capacity provided by mitochondria and aerobic metabolism. Nutrient cycles intensify as ecosystems become more dynamic. Organic matter flows through food webs with greater efficiency. Microbial decomposition recycles nutrients into forms that primary producers can use, supporting continuous productivity. Sedimentary basins capture organic carbon and phosphorus in quantities that influence long-term chemical cycles. The interaction between oxygen, nutrients, and organic matter creates a stable yet evolving environment that supports increasingly complex life. As ediacaran organisms populate seafloors and coastal regions, they modify sediments, stabilize surfaces, and alter local chemistry. Their bodies create microhabitats for smaller organisms and influence the flow of oxygen into underlying sediments. These biological-geological interactions contribute to new forms of ecosystem engineering, guiding the structure of early communities. Earth's atmosphere approaches oxygen levels capable of supporting more advanced metabolisms, preparing the planet for the next phase of biological expansion. Atmospheric oxygen interacts with sunlight to maintain a protective ozone layer, moderating ultraviolet radiation and supporting life in shallower waters. This protective layer encourages organisms to explore brighter, nutrient-rich environments near the surface. The rise of complex life stands as an interconnected process. Oxygen acts as the central driver, enabling high-energy metabolisms and the evolution of larger, more intricate organisms. Mitochondria supply the power for cellular innovation. Nutrient-rich environments foster growth and specialization. Deep ocean oxygenation expands habitats and stabilizes global biogeochemical cycles. The atmosphere evolves into a catalyst that supports biological complexity across continents and oceans. The Ediacaran world grows increasingly diverse as organisms explore new strategies for feeding, movement, and reproduction. Their forms illustrate early experiments in multicellularity that lay the groundwork for future evolutionary radiations. The combination of oxygen thresholds, symbiotic innovations, nutrient availability, and atmospheric evolution shapes a planet ready for a dramatic next step. The Cambrian expansion of life with hard skeletons, active predation, and rapidly evolving ecosystems. Around 541 million years ago, Earth enters a remarkable evolutionary chapter. Marine ecosystems begin to display an unprecedented surge in biological diversity, often described as the Cambrian expansion. Organisms across the planet explore new body plans, new modes of movement, and new ecological strategies with extraordinary speed on geological timescales. The oceans transform into vibrant environments filled with forms that carry the blueprints for much of later animal life. Rising oxygen concentrations prepare the foundation for this evolutionary burst. Through the late Proterozoic, oxygen gradually enriches surface waters and extends deeper into the oceans. This increased oxygen availability supplies the energetic capacity required for animals with larger bodies, active movement, and predatory behaviors. Aerobic metabolism provides high energy yield, supporting complex tissues such as muscles, sensory organs, and digestive systems with specialized regions. These innovations allow organisms to expand into diverse ecological roles. One of the most transformative developments involves the origin of hard body parts. Early animals begin to secrete mineralized shells, plates, and external skeletons using materials such as calcium carbonate and calcium phosphate. This innovation protects soft tissues, supports muscular attachment, and introduces a new dimension to ecological interactions. As shells and hard parts accumulate in sediments, they create a fossil record that reveals extraordinary detail about Cambrian life. Among the most iconic groups from this era are trilobites, arthropods with segmented bodies, jointed limbs, and complex compound eyes. Their exoskeletons display ornate patterns and diverse morphologies, ranging from streamlined swimmers to bottom dwellers with elaborate spines. Trilobites thrive in marine habitats across the globe and diversify into hundreds of lineages. Their fossils provide a rich archive of Cambrian ecology, evolution, and environmental conditions. Alongside trilobites, the oceans host a wide range of shelled organisms, including brachiopods, hyoliths, and mollusk ancestors. Their shells vary in shape and function, offering protection, structural support, and new feeding strategies. Shell-bearing organisms influence sediment structure, nutrient cycling, and the architecture of marine communities. Their presence brings greater complexity to ecological networks, supporting interactions that drive further diversification. The Cambrian oceans also produce the first large predatory animals with advanced sensory systems. Among these predators, Anomalocaris holds a central place in paleontological research, with grasping frontal appendages, a circular mouth lined with hard plates, and a streamlined body capable of swift movement. Anomalocaris becomes a formidable hunter. Its eyes feature tens of thousands of lenses, granting excellent visual acuity in well-lit waters. Such sensory and predatory systems represent major evolutionary innovations, shaping the behavior and morphology of prey species. As predators grow more sophisticated, prey organisms evolve new defenses. Hard shells, spines, burrowing behaviors, and rapid movement become increasingly common. This interplay between predator and prey fuels an evolutionary feedback loop, driving the emergence of new body plans, improved mobility, and enhanced sensory capabilities. The oceans fill with organisms navigating complex interactions that stimulate continuous diversification. Oxygen and evolution reinforce each other in powerful ways during the Cambrian expansion. Increased oxygen supports larger and more active animals. These animals stir sediments, alter habitats, and influence nutrient distribution through their feeding and movement. Bioturbation, the mixing of sediments by burrowing organisms, transforms the chemistry of seafloors. distributing oxygen deeper into sediments and creating gradients that support diverse microbial communities. These changes enhance nutrient recycling, stimulating primary production and reinforcing oxygen evolution feedbacks. Tectonic activity contributes strongly to Cambrian environmental conditions. Continental positions shift considerably during this time. Many land masses cluster near the equator, creating wide, shallow seas around continental margins. These warm, sunlit waters host abundant nutrients delivered by weathering of continental rocks. Large, epicontinental seas offer extensive habitats with conditions ideal for marine life, including stable temperatures, moderate salinity, and rich supplies of dissolved minerals. Climate during the Cambrian supports active biological systems. Greenhouse conditions maintain warm oceans that encourage high metabolic rates and rapid growth. Frequent storms circulate nutrients and stimulate planktonic productivity. Weathering of continental rocks delivers phosphorus and other key nutrients into coastal regions. These factors combine to produce ecosystems capable of sustaining large, complex animals across diverse environments. The fossil record from Lagerstätten sites such as the Burgess Shale in Canada and the Chengjiang Biota in China provides exquisite detail about life during this era. These formations preserve soft tissues with remarkable clarity, revealing the intricate structures of early animals. Gills, digestive tracts, appendages, and neural tissues appear in fine sedimentary layers. They illustrate the diversity of body plans, including early chordates, arthropods, priapulid worms, lobopodians, and many enigmatic forms with uncertain relationships to modern groups. These fossils highlight the experimental nature of Cambrian ecosystems. Animals explore a wide range of anatomical layouts: five-fold symmetry, bilateral symmetry, elongate worm-like forms, flattened discs, and tubular bodies. Each form reflects adaptive strategies tuned to specific habitats, feeding approaches, and modes of locomotion. This diversity establishes the foundations for modern phyla, linking Cambrian organisms to animals that inhabit today's oceans, rivers, and land environments. As ecosystems grow more complex, energy flows through food webs with greater efficiency. Planktonic producers supply organic matter to filter feeders, grazers, and suspension feeders. Predators consume these organisms, redistributing nutrients and shaping community structure. Decomposers break down organic matter, returning nutrients to the environment and fueling further productivity. This cyclical flow supports stable yet dynamic ecosystems capable of supporting large populations and diverse taxa. Chemical signatures from Cambrian sediments show increased oxygen levels in both surface and mid-depth waters. These signatures appear in iron and sulfur isotopes, trace metal concentrations, and the distribution of redox-sensitive minerals. Such geochemical markers reflect oceans with stratified oxygen gradients that sustain aerobic organisms at multiple depths. This oxygen structure supports active swimming animals and promotes evolutionary radiations across trophic levels. The Cambrian expansion illustrates the power of environmental and biological interplay. Oxygen concentration, nutrient supply, tectonic configuration, and evolutionary innovation combine to produce an extraordinary burst of complexity. Each factor reinforces others, creating a cascade of changes that alter the trajectory of life on Earth. The oceans evolve from primarily microbial ecosystems into environments with diverse, visually rich communities of animals that swim, crawl, burrow, hunt, and interact in ways unseen during earlier eras. Through these developments, early animal life establishes the frameworks for later evolutionary chapters. Body plans stabilize into recognizable forms. sensory systems advance, skeletons and exoskeletons become widespread, ecological roles expand into niches that persist for hundreds of millions of years. The Cambrian world creates a template for future ecosystems, shaping the evolutionary landscape for the rise of vertebrates, coral reefs, and the complex food webs that characterize the Phanerozoic eon. The Cambrian expansion represents a profound transformation in Earth's history. It showcases the influence of oxygen on biological evolution, the importance of continental arrangements, the impact of nutrient cycles, and the creative power of evolution operating through feedback between organisms and their environment. Through this era, Earth becomes home to a flourishing diversity of life with forms that echo across geological time. Around 470 million years ago, Earth enters a transformation that reshapes climate, atmosphere, and the structure of ecosystems across the continents. Life, long established in the oceans, begins to explore terrestrial environments. The earliest pioneers include small, simple plant forms resembling modern liverworts and mosses. These organisms settle along shorelines and damp surfaces where water flows regularly from streams and coastal spray. Their presence prepares the land for a profound ecological shift. Early plants rely on spores transported by wind, allowing them to spread across broad regions. As they expand, they interact with rocks through chemical processes that influence weathering rates. Even small mats of early land plants contribute to the breakdown of minerals, enriching soils with ions such as calcium, magnesium, and potassium. These ions travel into rivers and oceans, influencing the chemistry of sedimentary basins and supporting nutrient cycles. Through millions of years, plants evolve structures that allow them to extend farther from water. Vascular tissues, xylem and phloem, emerge as conduits for transporting water, nutrients, and sugars throughout the plant body. These tissues grant plants the ability to grow taller and anchor themselves more firmly in soils. As vascular plants rise across the continents, landscapes begin to shift from bare rock surfaces to green expanses of stems and leaves. Roots represent one of the most influential innovations of this era. Early root systems penetrate rock surfaces, expanding cracks and altering minerals through chemical interactions. As roots grow deeper and become more extensive, weathering rates increase dramatically. This process draws carbon dioxide from the atmosphere through reactions between minerals and dissolved carbon. Over time, these reactions contribute to the burial of carbon in sediments, guiding long-term climate regulation. By the Devonian period, around 419 to 359 million years ago, forests with tree-like plants flourish. Giant club mosses, horsetails, and early ferns rise toward the sky, forming dense canopies that reshape humidity, temperature, and soil structure. These forests create shaded understories, support decomposition processes, and foster new ecological interactions among terrestrial organisms. Fungi, arthropods, and early amphibians explore environments made rich by plant growth and organic matter. The expansion of forests enhances carbon burial through multiple pathways. Plants fix carbon dioxide during photosynthesis, storing carbon within their tissues. When forests grow rapidly, they accumulate large amounts of biomass. As plant material falls into wetlands and waterlogged soils, decomposition slows. Under these anoxic conditions, organic matter builds in thick layers. Over millions of years, this accumulation leads to extensive deposits that develop into coal. These coal-forming environments reach extraordinary scale during the Carboniferous period, beginning around 359 million years ago. Vast swamp forests stretch across equatorial regions, filled with towering lycopsids, broad-leaved ferns, and seed-bearing plants. Warm temperatures and abundant rainfall support rapid growth. Dense root networks stabilize sediments, creating peat-filled basins capable of storing enormous quantities of carbon. As forests drive carbon burial, atmospheric oxygen rises. Photosynthesis produces oxygen as a byproduct, and carbon burial prevents immediate recycling through decomposition. With large amounts of carbon locked in sediments, oxygen accumulates in the atmosphere. During the late Carboniferous, oxygen concentrations reach levels far higher than modern values. Estimates suggest atmospheric oxygen may have approached 30% or even slightly higher during peak intervals. High oxygen concentration influences animal physiology and evolution. Arthropods, with respiratory systems that rely on passive diffusion through tracheal tubes, flourish in this oxygen-rich environment. Many species grow to impressive sizes. Dragonflies with wingspans spanning more than 70 centimeters, over 27 inches, glide through forest canopies. Millipede-like arthropods stretch to lengths exceeding 2 meters, over 6 feet. These large forms arise because abundant oxygen supports efficient diffusion across their respiratory tissues. Insects explore the skies through flight, supported by muscular power and oxygen-rich air. Their diversity increases as flowering plants have not yet appeared, so forests remain dominated by spore-bearing species. Early amphibians also benefit from elevated oxygen levels, roaming wetlands and rivers with respiratory strategies suited to oxygen-rich environments. Forest ecosystems generate feedback loops that influence atmospheric composition. As plants grow, they absorb carbon dioxide, reducing greenhouse warming. With extensive carbon burial in coal-forming environments, atmospheric carbon dioxide decreases further. This shift encourages global cooling trends, contributing to climatic patterns that favour glaciation at high latitudes. Geological records from the late Paleozoic reveal signs of ice sheets forming in Gondwana, influenced in part by the interplay between plant-driven carbon burial and atmospheric chemistry. River systems carry plant debris, nutrients, and minerals into deltas and marine basins. These materials support diverse coastal ecosystems and influence carbonate formation. The chemistry of seawater changes as rivers deliver increased amounts of ions produced by weathering. Marine organisms, such as brachiopods, corals, and early echinoderms, respond to these changes with shifts in calcification patterns and evolutionary diversification. Continental greening influences marine life through these interlinked cycles. Forests also alter the hydrological cycle. Transpiration releases water vapor into the atmosphere, influencing cloud formation and regional precipitation. Dense vegetation increases humidity near the surface, creating microclimates within forest interiors. Soil formation accelerates as roots, fungi, and microorganisms break down minerals and organic matter. These soils support further plant growth, reinforcing the expansion of forests. Over millions of years, forests shift across continents in response to climate gradients, tectonic movements, and sea level changes. Their presence enriches the land with organic matter, increases biodiversity, and encourages the evolution of terrestrial food webs. Herbivorous arthropods adapt to plant tissues, developing strategies for chewing, piercing, and digesting cellulose. Carnivorous forms pursue these herbivores, creating complex terrestrial ecosystems supported by energy captured through photosynthesis. Coal deposits record the immense scale of Carboniferous swamp forests. These deposits appear in regions such as North America, Europe, and Asia, forming thick seams that represent millions of years of biological productivity. Coal formation demonstrates the enormous influence of terrestrial vegetation on global carbon cycles. Each layer illustrates a world where forests shape climate, atmosphere, and geology. As the Carboniferous period progresses, plant evolution continues. The first seed-bearing plants diversify, spreading across drier environments beyond swamp regions. Seeds introduce new reproductive strategies, allowing plants to colonize upland habitats and expand across wider terrains. Their presence marks another major step toward the ecological richness that will later support reptiles, insects, and diverse terrestrial ecosystems. The greening of the continents establishes Earth as a world dominated by photosynthesis, with plants directing global chemical cycles. Their roots alter landscapes, Their tissues store carbon. Their growth and decay influence atmospheric oxygen and carbon dioxide. Through these processes, forests transform air, climate, and life across the planet. This chapter reveals the profound influence of plants on Earth's evolution through vascular tissues, roots, carbon burial, and the interplay of swamps and oxygen-rich air. Forests reshape continents and oceans. These transformations prepare the planet for new biological expansions, including the rise of large terrestrial animals and the formation of ecosystems with increasing structural and behavioral diversity. Around 252 million years ago, Earth enters one of the most dramatic transitions in its entire history. Life on land and in the oceans reaches extraordinary diversity during the late Permian. Yet the planet carries conditions that move toward an immense environmental shift. Deep within the lithosphere, powerful mantle plumes rise toward the surface beneath what is now Siberia. These plumes supply vast amounts of magma that erupt through fractures across the region, creating one of the largest volcanic provinces ever recorded, the Siberian Traps. These eruptions persist for hundreds of thousands of years. Lava floods cover millions of square kilometers, hundreds of thousands of square miles, with layers of basalt that stack into sequences several kilometers thick. Volcanic gases pour into the atmosphere continuously. Carbon dioxide, methane, sulfur compounds, and halogens enter the air in volumes capable of reshaping global climate. The combined effects of heat, pressure, and gas release place enormous stress on ecosystems across the planet. Carbon dioxide accumulates in the atmosphere, creating a strong greenhouse effect. As concentrations rise, global temperatures increase significantly. This state of hypercapnia, elevated carbon dioxide levels, affects both climate and biological function. Warm air holds more moisture, producing intense rainfall in some regions and prolonged heat in others. Terrestrial plants struggle with altered gas exchange as carbon dioxide levels exceed the ranges most species experience during earlier eras. Oceans respond to these changes with increasing acidity. Carbon dioxide dissolves into seawater and forms carbonic acid, altering the pH of marine environments. Acidification influences the availability of carbonate ions, essential components for organisms that use calcium carbonate to build shells and skeletons. Reef-building species, plankton with mineralized structures, and many benthic organisms face increasing challenges as their environments shift chemically. Large volumes of volcanic gases enter the stratosphere, influencing atmospheric chemistry. Sulfur-rich aerosols reflect sunlight, contributing to short-term cooling phases that alternate with prolonged warming driven by carbon dioxide. Halogen compounds influence ozone chemistry, affecting ultraviolet radiation reaching Earth's surface. These fluctuations create complex patterns of climatic stress with global reach. As temperatures rise, oceans lose the ability to hold dissolved oxygen. Warm water carries less oxygen than cool water, and this reduction influences marine chemistry dramatically. Oxygen pore zones expand, spreading through mid-depth waters and across continental shelves. These conditions encourage microbial processes that release additional greenhouse gases, including methane and hydrogen sulfide. Stratified oceans, layers with limited mixing, reinforce these trends by trapping gases within deeper regions. Methane clathrates, crystalline structures that store methane within ocean sediments, respond to changing temperatures. As oceans warm, these clathrates destabilize, releasing methane into the water column and atmosphere. Methane carries extraordinary greenhouse potential, amplifying warming trends initiated by volcanic carbon dioxide. This feedback accelerates climatic change further, influencing ecosystems across the globe. Marine life faces immense challenges as oxygen levels fall, temperatures rise, and acidity increases. Many species rely on stable oxygen concentrations for respiration. With expanding low oxygen zones, habitats shrink dramatically. Sedimentary records from this time show widespread euxinic conditions, waters rich in hydrogen sulfide produced by microbial activity. These environments support specialized microbes yet present a chemical landscape that challenges most marine animals. The impact on biodiversity is immense. Roughly 90% of marine species vanish during this interval. Reef-building organisms, trilobites, many mollusk groups, and numerous planktonic species disappear from the fossil record. Food webs restructure as primary producers, invertebrates, and predators face extreme pressures. The seafloor changes from diverse communities with complex interactions to environments dominated by microbial mats and opportunistic survivors. Terrestrial ecosystems experience similar upheaval. Forests decline as heat stress, drought cycles, and atmospheric changes influence plant physiology. Many large herbivores and carnivores face shifts in food availability, habitat stability, and climate patterns. Wind-blown sediments accumulate across broad regions, leaving geological signatures that illustrate significant ecological transformation. Across both land and sea, the Great Dying marks a profound moment where environmental stress exceeds the adaptive capacity of many species. The combined influence of massive volcanism, greenhouse gas buildup, ocean chemistry shifts, and atmospheric changes creates one of the most intense extinction intervals known. Yet the planet also begins pathways toward recovery. After volcanic activity decreases and carbon burial resumes, atmospheric carbon dioxide gradually declines. Silicate weathering draws carbon from the atmosphere as minerals interact with water and carbonic acid. As carbon dioxide levels drop, global temperatures return to more moderate ranges. Oceans regain oxygen as circulation improves and temperature gradients strengthen. These shifts create conditions that support ecological renewal. During the early Triassic, life begins a slow process of diversification. Opportunistic species colonize newly available ecological spaces. Early ammonoids, bivalves, and conodonts display strong recovery potential in marine environments. On land, archosaurs, ancestors of crocodiles, pterosaurs, and dinosaurs, emerge within reorganized ecosystems. Plants also expand into regions once dominated by late Permian forests. New communities of ferns, seed plants, and conifers take root across floodplains and upland environments. The geological record from this period reveals large changes in sediment structure and mineral composition. Black shales rich in organic matter reflect intervals of low oxygen, while carbonate deposits that form later illustrate improvements in ocean chemistry. These sedimentary sequences help scientists reconstruct climatic and ecological changes across millions of years. Recovery after the Great Dying inspires research into the resilience of life. Even during profound environmental stress, evolutionary processes continue. New adaptations arise in response to altered climates and chemical conditions. Body plans, feeding strategies, and reproductive methods diversify across surviving lineages. The ecological turnover that follows extinction produces communities with structures that differ significantly from those of the late Permian. Through these processes, Earth moves toward an era that will eventually support dinosaurs, early mammals, and the complex ecosystems of the Mesozoic. The Siberian Traps eruptions demonstrate the immense influence of geological forces on the biosphere. They highlight the interdependence of volcanic activity, atmospheric chemistry, ocean circulation, and biological evolution. Through this event, Earth displays both extraordinary vulnerability and extraordinary resilience. The Great Dying stands as a reminder of the profound power embedded within planetary processes, shaping the trajectory of life across deep time. The Mesozoic era, spanning roughly 252 to 66 million years ago, unfolds as a time of remarkable warmth, dynamic climates, and continents that shift steadily across the globe. The atmosphere plays a central role in this story. Carbon dioxide levels remain high across much of the era, creating greenhouse conditions that support lush forests, widespread deserts, and warm oceans. These environments host the rise of dinosaurs, marine reptiles, early birds, and flowering plants, forming ecosystems that display extraordinary diversity and longevity. High carbon dioxide concentrations influence temperature, precipitation, and ocean chemistry. Warm oceans circulate heat efficiently, spreading stable climates across vast regions. Polar areas support forests with thick canopies, and temperate regions extend far into latitudes that today carry snow and ice. Tropical belts produce abundant rainfall in some regions and arid conditions in others, depending on continental placement and ocean currents. These variations shape habitats across which dinosaurs evolve. Oxygen levels fluctuate throughout the Mesozoic, creating physiological environments that influence respiratory strategies, growth patterns, and metabolic rates. Many dinosaur groups display adaptations that align with changes in atmospheric composition. Large sauropods carry extensive air sac systems connected to their lungs, improving oxygen extraction and reducing body density. Theropods, including early ancestors of birds, develop flow-through lung structures that channel air continuously across respiratory surfaces. These systems allow efficient gas exchange and support active lifestyles, even in climates marked by shifting oxygen levels. The interplay between atmosphere and physiology encourages evolutionary experimentation. Dinosaurs grow to enormous sizes, with sauropods reaching lengths exceeding 30 meters, over 98 feet, and weights that rival modern whales. Their respiratory systems circulate oxygen effectively across massive bodies, supporting high growth rates and sustained activity. Predatory dinosaurs develop strong muscular systems and advanced sensory organs that function fluently in warm, oxygen-rich environments. Continental drift exerts major influence on Mesozoic climate rhythms. At the beginning of the era, most land masses join into the supercontinent Pangaea. This giant landmass stretches across equatorial, temperate, and polar zones, creating extensive interior deserts and strong seasonal variations. As tectonic forces reshape the planet, Pangaea breaks apart into Laurasia in the north and Gondwana in the south. These continents move steadily across latitudes, altering ocean gateways, circulation patterns, and atmospheric flow. As the Atlantic Ocean begins to open, new coastlines experience warm currents and increased humidity. Monsoon systems strengthen around large continental masses, producing seasonal rainfall that enriches ecosystems and supports diverse vegetation. Vast conifer forests, cycads, ginkgos, and early flowering plants spread across habitats shaped by climatic rhythms tied to ocean-atmosphere interactions. The Jurassic period, around 201 to 145 million years ago, displays particularly stable climates that support giant sauropods, stegosaurids, and a rich array of marine reptiles. Warm seas host ammonites, ichthyosaurs, and plesiosaurs. Coastal regions provide extensive wetland habitats where dinosaurs, early mammals, and pterosaurs follow migration routes shaped by seasonal patterns. By the Cretaceous period, around 145 to 66 million years ago, the planet enters an even stronger greenhouse phase. Carbon dioxide levels rise further, sea levels climb, and shallow epicontinental seas spread across continents. These warm, nutrient-rich waters support vast populations of plankton that influence carbon cycling and atmospheric chemistry. Chalk deposits, formed from the remains of coccolithophore algae, accumulate across regions of Europe, Asia, and North America, offering geological evidence of high biological productivity. The Cretaceous greenhouse world carries lush tropical forests, temperate woodlands, and vast coastal plains. Flowering plants evolve and diversify rapidly, attracting insects that co-evolve with complex pollination strategies. Herbivorous dinosaurs explore these landscapes, developing specialized jaws and digestive systems tailored to tough vegetation. Hadrosaurs develop intricate dental batteries, while ceratopsians evolve powerful beaks and frills. Carnivorous dinosaurs, including tyrannosaurids and dromaeosaurids, adapt to new prey and changing ecosystems. Atmospheric conditions of the Cretaceous period support rapid growth rates in many dinosaur species. Bone histology reveals rings of tissue that indicate continuous growth, supported by active metabolic processes. Abundant oxygen and warm climates contribute to these growth patterns. Fossil trackways show herds of large herbivores traveling across floodplains, while predators follow migration routes shaped by vegetation cycles and seasonal water availability. Ocean chemistry during the Cretaceous carries its own rhythms. Warm waters promote strong stratification, with surface layers rich in oxygen and deeper layers influenced by nutrient cycling and microbial activity. Marine reptiles flourish in these conditions, displaying powerful flippers, streamlined bodies, and advanced visual systems suited for warm, well-lit waters. By the late Cretaceous, continents continue to drift toward configurations that resemble modern arrangements. These shifts alter climate zones, ocean circulation, and the distribution of ecosystems. The Western Interior Seaway in North America, for example, divides the continent into eastern and western land masses, creating coastal environments rich in marine life and supporting diverse terrestrial ecosystems along its margins. Into this dynamic world, a new force arrives from space. Around 66 million years ago, a large asteroid enters Earth's atmosphere and strikes near what is now the Yucatan Peninsula. The impact releases energy on a scale far greater than any volcanic eruption or tectonic shift. A crater more than 180 kilometers, over 112 miles, in diameter forms instantly. Shock waves radiate outward, ejecting vaporized rock and molten droplets into the atmosphere. Atmospheric rhythms shift abruptly. Ejecta rise into the stratosphere and spread globally. Sunlight passes through layers of dust, aerosols, and sulfur-rich compounds with increasing difficulty. Photosynthesis declines rapidly as light availability decreases. This decline influences both terrestrial and marine food webs. Surface oceans cool as planktonic productivity falls, and nutrient cycles shift dramatically. Thermal radiation from re-entering ejecta contributes to widespread fires, which influence atmospheric chemistry by injecting soot and carbon compounds into the air. Short-term warming pulses transition into prolonged cooling phases as aerosols reflect solar radiation. This combination of rapid heating and extended cooling influences ecosystems across all continents. The impact initiates a period of atmospheric collapse in terms of biological support. Plants experience reduced photosynthesis, herbivores encounter declining food supplies, and predators face diminishing prey populations. Marine environments experience declines in plankton, which ripple across food webs. Many species vanish from the fossil record as these atmospheric changes unfold. Yet Earth continues its cycles of renewal. Surviving species adapt to new conditions, occupying ecological spaces that open during the transition. Birds, descendants of theropod dinosaurs, take advantage of changing environments and diversify across continents. Mammals explore niches shaped by altered vegetation and climate. The atmosphere gradually clears as aerosols settle and chemical cycles stabilize, supporting new ecosystems with forms that guide the Cenozoic era. The Mesozoic stands as a powerful testament to the influence of atmospheric rhythms on life. High carbon dioxide supports warmth and biodiversity. Oxygen fluctuations shape physiology and evolutionary strategies. Continental drift guides climate zones and ecological opportunities. A greenhouse world encourages growth and diversification, while an asteroid impact delivers an abrupt atmospheric transformation that ends the reign of the dinosaurs and shapes the future of life on Earth. Around 2.6 million years ago, Earth enters the Quaternary period, a chapter defined by rhythmic expansions and retreats of great ice sheets across the northern hemisphere. These cycles create powerful climatic pulses that reshape landscapes, influence ocean circulation, and guide the evolution of many species. Ice advances across continents, sometimes reaching latitudes that today carry forests and farmland. During warmer intervals, vast meltwaters return to the oceans, shifting coastlines and climate zones. At the heart of these fluctuations lies a set of astronomical influences known as Milankovitch cycles. These cycles describe variations in Earth's orbit and rotational geometry that unfold over tens of thousands of years. They influence the distribution of sunlight across seasons and latitudes, guiding the growth and retreat of ice sheets with striking regularity. The first component, eccentricity, measures the shape of Earth's orbit around the Sun. Over cycles of roughly 100,000 years, the orbit shifts from more circular to more elliptical forms. These changes alter the distance between Earth and the Sun during different parts of the year, influencing the total amount of solar energy Earth receives annually. Even small variations in solar input exert strong effects when amplified by the planet's climate system. The second component, obliquity, describes the angle of Earth's axial tilt. Over a cycle of about 41,000 years, this tilt moves through a range that influences the contrast between seasons. A larger tilt produces stronger seasons with warmer summers and colder winters. A smaller tilt creates milder seasonal contrasts. Ice sheets respond strongly to summer temperatures. Warmer summers encourage melting, while cooler summers favour ice preservation and gradual expansion. The third component, precession, governs the slow wobble of Earth's rotational axis. Over a cycle of roughly 23,000 years, this wobble shifts the timing of seasons relative to Earth's position in its orbit. Precession influences which hemisphere experiences stronger summer sunlight and affects monsoon systems, continental climates, and the distribution of heat across the planet. Together, these cycles guide an intricate climatic rhythm. During periods when orbital settings encourage cooler summers in the northern hemisphere, ice accumulates year after year. Snowfall compacts into ice, forming sheets that expand across large regions. Glaciers flow outward from high-latitude centres, sculpting landscapes through erosion, transporting sediments, and carving deep valleys. During intervals of warmer summers and stronger solar input, ice retreats and interglacial climates emerge. Carbon dioxide plays a strong role in these transitions. During glacial advances, carbon dioxide concentrations in the atmosphere decrease as oceans absorb greater quantities of dissolved carbon. Colder waters hold more carbon dioxide, and ocean circulation patterns deliver this carbon into deep basins. As ice sheets grow and sea levels fall, continental shelves emerge, influencing the exchange of gases between atmosphere and ocean. Lower carbon dioxide reduces greenhouse warming, reinforcing glacial conditions. During interglacial phases, warming oceans release carbon dioxide into the atmosphere. This release enhances greenhouse warming, creating feedback loops that support further ice retreat. These carbon dioxide variations record Earth's climate in ice cores from Antarctica and Greenland, revealing rhythmic patterns that mirror Milankovitch cycles. Each oscillation displays a strong relationship between orbital geometry, temperature, carbon dioxide, and ice volume. Dust plays an important role in glacial climates. During colder intervals, large regions experience reduced vegetation cover, exposing soils to wind erosion. As winds strengthen across open plains, dust enters the atmosphere in large quantities. This dust travels across continents and oceans, settling in thin layers on glaciers and ice sheets. Dust influences climate by altering the reflectivity of snow surfaces and by carrying iron that fertilizes marine ecosystems. Increased iron supply encourages phytoplankton growth, which influences carbon uptake and ocean chemistry. Temperature gradients between equator and poles increase during glacial phases. Stronger gradients guide atmospheric circulation, producing powerful wind systems and storm tracks. Ocean currents shift as ice sheets alter coastlines and circulation pathways. The Atlantic meridional overturning circulation, a major component of global ocean transport, responds to pulses of meltwater and salinity changes. These interactions influence temperatures across the northern Atlantic, shaping environments that support early human evolution. Within this dynamic climatic landscape, Homo sapiens emerges. Fluctuating temperatures, shifting rainfall patterns, and evolving ecosystems create conditions that encourage adaptability, innovation, and migration. Early humans experience forests that expand during warm intervals and retreat during colder phases, leaving grasslands that support large herbivores. These environments encourage new strategies for hunting, foraging, tool-making, and social cooperation. Interglacial cycles guide the distribution of habitats across Africa, Eurasia, and later the entire globe. During warm phases, rainfall increases in many regions, supporting lakes, rivers, and fertile landscapes. During colder phases, deserts expand while some regions develop cooler, wetter climates that favor different plant assemblages. Human movements follow these shifting ecological corridors. As climates change, populations discover new regions and resources, shaping the trajectory of human expansion. Ice sheets influence sea levels dramatically. During glacial maxima, sea levels fall by more than 120 meters, around 394 feet, exposing continental shelves and creating land bridges between continents. These land bridges connect Siberia to Alaska, Southeast Asia to Australia, and Britain to Europe. Each connection supports migrations of humans and other species. During interglacial periods, melting ice raises sea levels, flooding these land bridges and shaping the distribution of cultures and ecosystems. The interplay between temperature gradients, dust flux, carbon dioxide levels, and ocean circulation produces climates with strong variability. Each shift invites evolutionary responses from plants, animals, and early human populations. Some species adapt to cold tundra environments, while others thrive in temperate forests or savannas. These shifts influence dietary strategies, shelter design, and cultural development across human populations. Ice cores drilled from Antarctica reveal layers corresponding to hundreds of thousands of years. Air bubbles trapped within these layers record atmospheric gases directly, offering a precise picture of past climates. These cores display rhythmic curves representing carbon dioxide concentration, methane levels, and temperature variations. Each curve mirrors orbital cycles with striking clarity, demonstrating Earth's sensitivity to small astronomical influences amplified through powerful feedback mechanisms. Glacial periods showcase the immense influence of Earth's orbital geometry on global climate. Interglacial periods reveal the capacity of warming trends to reshape ecosystems and encourage migrations across continents. Together, these cycles create the climatic context in which Homo sapiens evolves, spreads across the globe, and eventually forms societies that reflect thousands of years of environmental change. Earth's climate during the Quaternary breathes in long, slow rhythms. Ice advancing, ice retreating, seas rising, seas falling. These movements shape coastlines, ecosystems, and the futures of countless species. Through these cycles, the planet displays a remarkable balance between astronomical forces, atmospheric chemistry, and the resilience of life. Around 11,700 years ago, Earth enters a period of remarkable climatic stability known as the Holocene. Glacial ice retreats from large parts of the northern hemisphere, sea levels rise toward modern positions, and seasonal cycles settle into patterns with moderate variability. This stability creates conditions that support the growth of forests, grasslands, wetlands, and river systems across continents. Humans, long accustomed to migratory lifestyles shaped by changing climates, discover opportunities for new ways of living. Agriculture emerges across multiple regions independently. Wheat and barley flourish in the Fertile Crescent. Rice spreads along East Asian river valleys. Maize thrives in the Americas, and sorghum and millet rise across African landscapes. The Holocene climate fosters predictable rainfall patterns and steady temperatures, encouraging the cultivation of plants and the domestication of animals. Villages grow into towns, towns into cities, and cities into networks of trade and cultural exchange. Human societies expand in scale and complexity through agriculture's reliable energy supply. As populations grow, humans influence landscapes with increasing intensity. Forests give way to fields, irrigation channels reshape river valleys, terraced hillsides expand across mountains. Fire becomes a tool for clearing land, shaping grasslands and woodlands across continents. These activities alter carbon storage in soils, influence biodiversity, and guide the structure of ecosystems. Through each action, humans become a significant ecological force. During the Holocene, Earth's climate displays natural variations, including warm intervals and cooler phases such as the Younger Dryas or the Little Ice Age. These fluctuations influence crop production, migration, and societal development. Yet the overall stability of the Holocene supports the long-term flourishing of civilizations from Mesopotamia to the Indus Valley, from the Nile Basin to the Andes, and across countless other regions. A major shift begins during the 18th century with the Industrial Revolution. Human societies harness energy stored in coal, oil, and gas, transforming economies and accelerating technological progress. As fossil fuels burn, carbon dioxide enters the atmosphere at rates far above natural background levels. This rapid rise influences Earth's radiative balance strongly, increasing the energy retained within the climate system. Instrumental records, ice core measurements, and atmospheric samples all reveal striking trends in carbon dioxide concentration over the past 2.5 centuries. In parallel, the anthropogenic nitrogen cycle expands dramatically. Industrial processes convert atmospheric nitrogen into ammonia on a massive scale, enabling modern fertilizers that support agricultural production across the globe. These fertilizers enhance crop yields and feed growing populations. They also flow into rivers, lakes, and coastal zones, influencing nutrient cycles, algal blooms, and oxygen levels in aquatic ecosystems. The scale of human-driven nitrogen fixation surpasses natural biological nitrogen fixation on land, guiding both terrestrial and marine chemistry. As industrial activities accelerate, humanity enters a period often described as the Anthropocene, a geological interval shaped by human actions. Researchers identify an array of markers that future scientists may recognize in sediments and rock layers. Plastics distribute across oceans, rivers, and soils, forming particles that embed within sedimentary deposits. Concrete accumulates across continents, creating a durable layer that records construction patterns and urban expansion. Radionuclides from mid-20th century nuclear testing form global signatures in ice cores, soils, and marine sediments. Each of these materials offers geological evidence of human influence on Earth's surface. Atmospheric changes reflect this influence vividly. Carbon dioxide, methane, and nitrous oxide concentrations rise in tandem with industrialization, transportation, and agricultural practices. Satellite observations reveal shifts in Earth's energy balance and track temperature changes across continents and oceans. These trends influence precipitation patterns, storm intensity, sea ice extent, and wildfire activity. Climate zones migrate toward the poles, reshaping ecosystems across large regions. Oceans respond powerfully to these changes. They absorb a substantial portion of anthropogenic carbon dioxide, altering pH through the formation of carbonic acid. This acidification influences organisms that rely on carbonate structures, including corals, mollusks, and many planktonic species. Calcium carbonate saturation levels shift, guiding patterns of reef growth and distribution. Ocean warming enhances stratification, influencing nutrient cycles and oxygen content across depth layers. Marine heat waves, documented through extensive temperature records, influence coral reefs, kelp forests, and fish populations. Shifts in ocean currents alter migration routes for marine mammals and seabirds. Expanding low-oxygen zones influence coastal communities and fisheries, shaping ecological dynamics across oceans. Terrestrial environments respond with equal complexity. Rising temperatures influence plant flowering times, species ranges, and the frequency of droughts. In many regions, forests experience increased stress through heat waves, insect outbreaks, and altered precipitation patterns. Grasslands shift in composition as climate variables guide seedling establishment and soil processes. Human societies adapt to these changes through technology, infrastructure, and policy. Agricultural practices shift in response to temperature variations and water availability. Coastal cities plan for sea level rise, while inland regions adjust to altered rainfall patterns. Renewable energy spreads across grids, enhancing the diversity of Earth's energy systems. Remote sensing technologies reveal expanding fingerprints of human influence. Nighttime lights trace urban networks. Satellites track atmospheric aerosols, water vapor, vegetation growth, and glacial retreat. High-resolution measurements document thinning ice sheets in Greenland and Antarctica, shifts in monsoon systems, and soil moisture changes across continents. These data sets form the foundation for scientific understanding of Earth's evolving climate. Biodiversity responds dynamically to Anthropocene conditions. Some species expand their ranges through warming climates and altered habitats. Others follow shifting vegetation patterns or migrate toward cooler latitudes and higher elevations. Many ecosystems experience restructuring as species assemble in new combinations. Pollinators interact with flowering plants across changing seasonal cycles, influencing agriculture and wild habitats alike. Through these developments, humanity becomes a geological force. The global carbon cycle responds to industrial emissions. The nitrogen cycle responds to fertilizer production. Sedimentary layers record plastics, metals, and industrial byproducts. Lakes and oceans carry chemical signatures of modern agriculture and energy use. Glacial ice records atmospheric gases through tiny bubbles trapped in each yearly layer. Human fingerprints weave across each component of Earth's system. Yet the Holocene's legacy remains visible. Its stability enabled the rise of agriculture and the formation of civilizations, shaping languages, cultures, and technologies. The Anthropocene emerges from this foundation, guiding Earth into a period where human influence joins tectonic forces, orbital cycles, and volcanic processes as major drivers of planetary change. Earth's atmosphere, oceans, and biosphere continue to respond to evolving human-environment interactions. The planet experiences shifts in temperature, precipitation, ice cover, and biodiversity that unfold across decades and centuries. Through these transformations, humanity observes planetary rhythms once guided solely by natural cycles and now shared with industrial and technological forces. This era reveals the profound influence of human activity on deep time processes, shaping the future of Earth's climate and ecosystems. Earth moves steadily through deep time, guided by forces that unfold across hundreds of millions of years. Tectonic plates drift, continents rise and erode, and oceans shift across the surface. Above all these processes, the sun's slow evolution shapes the planet's future in ways that extend far beyond human timescales. As the star brightens, Earth's long-term carbon cycle responds, guiding the planet toward a gradual decline in biological activity. Silicate weathering plays a central role in this process. Rainfall interacts with exposed minerals, forming weak acids that dissolve silicates in rocks. This reaction draws carbon dioxide from the atmosphere and delivers it into rivers and oceans, where it eventually becomes stored in carbonate sediments. Over millions of years, this mechanism regulates Earth's temperature. A warmer climate accelerates weathering, drawing down carbon dioxide and encouraging cooling. A cooler climate slows weathering, allowing carbon dioxide to accumulate and encouraging warming. Through this feedback, Earth maintains a balance that supports life across vast spans of time. As the sun ages, its luminosity increases gradually. The warming influence raises evaporation rates, strengthens rainfall, and accelerates silicate weathering across continents. This enhanced weathering draws carbon dioxide to lower and lower concentrations. Plants depend on carbon dioxide for photosynthesis, and many species thrive at levels far above modern values. Over tens to hundreds of millions of years, carbon dioxide levels reach thresholds that challenge the growth of large, complex plants. C3 photosynthesis, used by most trees, shrubs, and temperate plants, requires relatively high carbon dioxide concentrations. As concentrations fall, C3 plants face increasing stress during respiration and growth. Grasses and other species that use C4 photosynthesis display greater tolerance for low carbon dioxide. These plants flourish across warm, dry environments and dominate the landscape during late stages of Earth's temperate evolution. As carbon dioxide continues its geological decline, even C4 plants experience limits. The global biosphere becomes simpler. Forests give way to open grasslands. Grasslands transition into sparse shrublands. Eventually, vegetation becomes dominated by small, hardy species that rely on efficient carbon-concentrating mechanisms. The richness of Earth's ecosystems diminishes gradually, guided by the interplay between sunlight, temperature, and atmospheric chemistry. The sun, meanwhile, continues its slow brightening. Higher luminosity increases surface temperatures, influencing oceanic evaporation significantly. Water vapor enters the atmosphere in larger quantities, creating a strong greenhouse influence. Increased humidity guides more intense rainfall in some regions and extended dry cycles in others. Over long timescales, the combined warming from solar evolution and water vapor feedback expands the planet's energy budget. As oceans warm, the rate of evaporation rises further. Atmospheric water vapor increases, influencing radiation transfer in the upper atmosphere. At certain thresholds, hydrogen begins to escape into space through photodissociation. This gradual loss of hydrogen leads to a slow decrease in Earth's total water inventory. Oceans shrink over millions of years as evaporation exceeds the return of liquid water to the surface. Life experiences increasing stress under these conditions. Plants, animals, and microbes adapt as long as ecological niches remain stable. Yet the long-term trend points toward environments with rising temperatures, expanding deserts, and reduced freshwater availability. Complex food webs yield gradually to simplified communities dominated by thermophilic and drought-tolerant species. Microbial life displays extraordinary resilience in many environments, including deep subsurface regions where conditions remain stable for extended periods. As temperatures climb, the continents warm extensively. Mountain glaciers vanish. Polar regions transform into temperate zones. Rivers shrink as moisture returns to the atmosphere more quickly than landscapes can capture it. The oceans lose volume steadily, retreating from continental shelves and leaving behind salt-rich basins. Shallow seas evaporate under intense heat, forming mineral deposits that create new geological layers. The continued brightening of the sun guides Earth toward a phase in which the planet enters a moist greenhouse state. In this phase, large amounts of water vapor rise into the upper atmosphere. Water molecules encounter intense ultraviolet radiation and separate into hydrogen and oxygen. Hydrogen escapes into space readily due to its low mass. Oxygen accumulates temporarily, but eventually reacts with surface materials and volcanic gases. Through this process, Earth's water inventory declines further. As oceans shrink, surface temperatures increase steadily. Vast dry regions cover most of the continents. Atmospheric dust rises from arid surfaces and circulates globally, influencing the scattering of sunlight and guiding new climate patterns. Microbial life persists in sheltered environments, such as deep soil layers, rock pores, and subsurface aquifers, where temperatures remain conducive to biochemical activity. A threshold arrives when liquid water no longer remains stable on the surface. At this stage, Earth transitions from a blue planet with thriving oceans to a world dominated by rock, salt deposits, and shrinking basins of concentrated brine. The atmosphere becomes enriched with water vapor and oxygen produced through photodissociation, but the balance shifts frequently as gases interact with geological processes. The biosphere enters its final stages, composed primarily of microbial species adapted to extreme heat and scarcity. Eventually, silicate weathering slows as continents dry. Carbon dioxide accumulates again through volcanic output, although levels remain influenced strongly by the diminishing biosphere. Photosynthetic processes decline sharply as plant life reaches its limits. With low carbon dioxide and high temperatures, the energy available to biological systems decreases substantially. The planet approaches a stage where photosynthesis operates only in specialized microorganisms capable of extreme efficiency. As the oceans complete their long retreat into the atmosphere and then into space, Earth transitions toward a barren state. The surface resembles a vast desert world with broad salt plains, volcanic terrains, and atmospheric conditions shaped primarily by solar radiation. The atmosphere thins in water content as hydrogen continues its slow escape. Oxygen gradually combines with minerals and volcanic gases, declining over extended geological intervals. During these final chapters of habitability, life remains present deep underground, in pockets where temperature and moisture align within favorable ranges. Microbial communities adapt to high pressures, mineral-rich environments, and chemical energy sources that persist beneath the surface. These subterranean ecosystems continue as long as geothermal processes maintain environments with suitable conditions. Eventually, the sun's luminosity reaches levels that exceed the thresholds for any form of liquid water on Earth's surface or near-surface regions. The biosphere contracts into increasingly isolated microhabitats until even these refuge zones cross thermal limits. The final atmosphere evolves through interactions between solar radiation, surface minerals, and diminishing volcanic output. Over time, Earth becomes a quiet, barren world, shaped by wind, heat, and geological activity alone. Long before the sun expands into a red giant, Earth completes its long evolutionary arc. From molten origins to oceans, forests, animals, and civilizations, the planet supports life for billions of years. Through silicate weathering, solar evolution, atmospheric chemistry, and biospheric changes, Earth follows a path toward eventual silence. This final chapter reflects the deep time rhythms that guide planetary evolution. Earth breathes across billions of years, slows through the decline of carbon dioxide, and eventually reaches a stillness shaped by the physics of stars and the chemistry of rocks. Its legacy lives in the geological record, in the minerals formed by ancient oceans, in the fossils of forests and animals, and in the atmosphere that once carried the breath of life.